Welcome to springlib.
All right, so we've got basically these aldol uh, reactions. Okay, what that means is that we're going to either um, abstract one of these alpha hydrogens, right, and create an enol, and that enol is going to attack one of our two carbonyl carbons, right? And generally, what you want to do is consider when this is intramolecular, what ring size you're going to generate when this happens, right? Because whatever gives you the most favorable ring size is going to be the route that you'll proceed. Meaning, if this gets abstracted and attacks, right, then this is like carbon 1, 2, 3, 4, we get a 4-membered ring. That's not very great, right? If this hydrogen gets abstracted and we attach it here, right, we get a 1, 2, 3, 4, 5, 6-membered ring, right? So that's the most likely product, right? So that's how I know that we want to think about this hydrogen getting abstracted by a base. Okay. And we create our enolate. And it is at this point that this will swing down. We'll attack the carbonyl over here. This will swing up. And then we get our 6-membered ring, right? And if it helps, we can number these 1, 2, 3, 4, 5, 6. So basically, we could just draw any old 6-membered ring. Doesn't matter which. And we just know that there's going to be a carbonyl on carbon 2. So maybe we'll number these 1, 2, 3, 4, 5, 6. Okay, so we know we have a carbonyl on carbon 2. Okay, and we know that carbon 6 has an alkoxide. Okay, and that's really all we have to worry about for this reaction, right? And then at this point, we've got H3O plus, which we can say, okay, maybe it's like this. Okay, and so we can see protonation, for example. There we go. If we're so interested, I don't know, I guess it really depends on how your teacher's been teaching this. We can push this forward with the E1CB, that is elimination of the OH, right? In which we say that, okay, the next step after we've, oops, this is not water. This is supposed to be water, not acid. My bad. Okay. Okay, since we've regenerated hydroxide at this point, we may continue forward. Okay, and do something like this. Okay, we don't want, this is the only context in which we ever see OH as a leaving group, by the way. And so finally, our final product looks like this, alpha beta unsaturated ketone. Okay, it really depends on what your teacher, where they want you to stop, either at the alcohol or at the unsaturated ketone. I have no way of knowing that because sodium hydroxide and heat can mean either one or lead to either one. Okay. And basically, it's the same thing over here. Okay. Same idea. I guess in this case, we're definitely going to stop at the alcohol because we don't have heat and we don't have, yeah, basically. And we're doing an acidic workup afterward. Okay. Recall that because we have esters, right, that kind of forces us to only have one option in terms of which side of Well, we only have one alpha hydrogen, right, that we can consider. Right? There's only one location that can be deprotonated by the sodium ethoxide, is what I mean to say. Deprotonation, formation of the enolate. Okay, these electrons will swing back down. These will swing up. And at this point, it would be prudent to number the carbons. 1, 2, 3, 4, 5, 6, 7. So we're making a 7-membered ring. Okay. We'll give ourselves a little more space. We'll move down here. Still got our benzene. Okay, but now we've got 1, 2, 3, 4, 5, 6, 7. Okay, looks good. Let's number these. 1, 2, 3, 4, 5, 6, 7. Okay, we know that carbon 1 has a single bond to an oxygen. Sorry, single bond to a carbon. That's a double bond to an oxygen and a single bond to an ethoxide. Okay, we know that carbon 7 now has an alkoxide as well as a bond to an ethoxide. Okay. And at this point, the protonation, right, is just going to protonate our alkoxide and give us the alcohol instead. What does that look like mechanistically? Probably good to draw. There's a lone pair on this alkoxide, and it will grab a proton. There we are. That's the final product.